I was 10 years old in the back seat of a car. It was dark. I held a Game Boy close to my face because the streetlights were the only lamp I had. Wild Geodude showed up, and I did the same thing I always did. Name it. Rock and ground. The moment I recognized it, the problem felt smaller. That is the feeling Pokémon sells. The label comes first, and that sequence produces a feeling of control. Here's what I didn't expect. A 2019 fMRI paper in Nature Human Behavior found that childhood Pokémon players still show a distinct Pokémon signature in visual cortex as adults. It's a measurable response pattern. Now, here's the stakes, or the reason I'm explaining all of this to you. In adult life, you can label the problem correctly and still be stuck. You call it scope creep. The label's right, and the work still doesn't move. Because sometimes the label is not the solution. Sometimes recognition is the trap. Here's my promise to you. By the end of this episode, you will understand why Pokémon makes labeling feel like solving, what the brain data actually shows, and how to spot the moment you need adaptation instead of recognition. This episode is built around a 2019 paper in Nature Human Behavior by Jesse Gomez, Michael Barnett, and Grill-Spector. The title says exactly what they tested. Extensive childhood experience with Pokémon suggests eccentricity drives organization of visual cortex. Here's the basic claim of the paper. Childhood visual experience can shape where categories live in visual cortex decades later. They use functional MRI, or fMRI, to test it. The fMRI tracks small changes in blood flow. When a region works harder, blood flow usually goes up and lights up that portion of the brain. They scanned 22 adults. 11 were experienced Pokémon players. They started the original Game Boy games between ages of 5 and 8. They played heavily through childhood. The other 11 were novices. They had never played before. In the scanner, participants watched short blocks of images. Each block lasted for 4 seconds. Each block showed 8 images from one category. That is 2 images per second. They cycled through 8 categories: faces, headless bodies, animals, cartoons, pseudo words, cars, corridors, and Pokémon sprites from the original game. Everyone performed a simple oddball task the entire time, which means they pressed a button that kept attention steady. That kept the scan from turning into a Pokémon memory test. After scanning, the participants took a quick naming test. 40 original game Pokémon, 5 choices per item. Experienced players could name them. Novices generally could not. A subset of 6 experienced participants also completed retinotopic mapping, which is a map of vision on the brain. It tells you which regions prefer the center of gaze versus the edges. We need a few terms. I'll keep them tight. The ventral visual stream is the system that answers one question. What is this? As information moves along that stream, it reaches ventral temporal cortex. You can think of this as the brain's category shelf. Faces go here, words go here, bodies go here, places go here. It follows a visual constraint, which is basically retinal eccentricity. It's how far something is from the center of your gaze. Center vision is sharp, side vision is blurrier. The brain keeps that split. On the outer side of ventral temporal cortex, you mostly find categories you look at directly. Faces, words, small objects. Closer to the middle, you mostly find categories that fill the visual field. Scenes, rooms, corridors. 2 landmarks to help you orient inside the brain. The fusiform gyrus here, which is highlighted in yellow, is a ridge of cortex that often responds strongly to faces and words. And this is the occipitotemporal sulcus, which is biased towards your central vision. These are the things that you perceive directly and closely. And that's where that information is stored. So this is all the anatomy that we need. Pokémon gave the researchers a rare natural experiment. Kids all over the world did the same thing. They stared at a small screen, they kept the characters near the center of gaze, they repeated that for years. Pokémon characters are also made for individuation. That means telling similar things apart. Pidgey is not a Spearow, Poliwag is not a Poliwhirl. That repeated need to discriminate under consistent viewing conditions is the point. They tested two things. First, does the brain carry Pokémon information at all? Second, where does that information show up? They did not just look for bright spots, they analyzed patterns. Here's one of the terms that matters: voxel. A voxel is a tiny cube in the brain image like you see here. It is like a three-dimensional pixel. An fMRI scan is made of thousands of these cubes, and each cube has a signal. That signal shifts with blood flow, and multivoxel, meaning many voxel, pattern analysis asks a simple question. If you look at the pattern across many cubes at once, can you tell what the person is seeing? They also used careful region selection. They defined a Pokémon region from the experienced group using leave one out analysis. They left one participant out. They defined the region using the rest. Then they tested it on the held out participant, and that avoids circular analysis. So they ran two follow-ups. One tested specificity. Some experienced participants viewed Pokémon map scenes. They also viewed pixelated faces created by downsampling. And downsampling just means lowering the resolution of the image. The question was simple. Does the Pokémon region respond to anything Pokémon related? Or does it respond to the learned character category itself? The second follow-up tested visual field bias. That is the retinotopic mapping that I referred to earlier. It estimates whether a region prefers the center of the gaze or the edges. So here's what the scans showed. The experienced players showed a distinct, repeatable response to Pokémon in the ventral temporal cortex. Novices didn't. And this was not a general game effect. This was not a cartoon effect. It was specific to Pokémon characters. The response also landed in a consistent place, near the occipitotemporal sulcus, lateral to the fusiform gyrus. So why do the locations of these scans matter? Because the location is the result. Pokémon selectivity appeared in cortex biased toward central vision. The follow-up mapping supported that. This supports the paper's core hypothesis, eccentricity bias. The brain organized the category based on how it was viewed during childhood: small, central, repeated. The organizing constraint was visual experience during development. This is the key interpretation. The brain learned perceptual discrimination under consistent viewing conditions. It learned that uncertainty can be reduced through high-resolution discrimination. That is a perceptual skill. This falls under perceptual learning. Practice changes what you notice. Practice increases discriminability. Recognition here is fast classification. You see a thing, you place it in a known category. Decisions get simpler. Pokémon is built to reward that step. In the brain, that speed is a largely ventral visual stream plus basal ganglia reinforcement, where dopamine favors whatever reduces uncertainty quickly, even when the reduction is only perceptual. Pokémon did not invent the instinct to categorize, but it does give that instinct a clean gym. It pays you every time you turn uncertainty into a label. Pokémon rarely forces reevaluation after classification. Type effectiveness doesn't drift. The rules don't change mid-fight, so the game applies less pressure on a different skill. Monitoring. Monitoring is noticing when your current approach is no longer working as well as it did. Neuroanatomically, that kind of monitoring leans on anterior cingulate cortex for conflict and error signaling, and dorsolateral prefrontal cortex for holding an alternative rule set online long enough to switch. For our purposes, the paper's discussion stops there. What we have to say in the rest of the video is beyond the scope of the paper. What we've shown is that there's durable reorganization in a specific visual region. It doesn't claim this changes reasoning everywhere. That's where our discussion begins. The real question is this: what happens when a recognition-trained brain enters environments where correct labels don't stabilize outcomes? A new job, a slipping project, a team that stopped responding the way it used to. And in these settings, labeling the situation correctly can still leave you stuck. The failure is misplaced confidence. The instinct becomes simple. If things go wrong, the label must be wrong. Sometimes it's true. In other situations, the label's correct. The approach is stale, the environment moved, a simple diagnostic helps. But if a label changes what you say but not what you do, you're not really adapting, you're just narrating. And Pokémon is efficient training. It trains recognition extremely well. The risk is assuming the same loop solves every problem. You don't need to unlearn recognition. You need a second check. You just have to ask one question: is my current approach still paying off? This is called monitoring. Pokémon rewards recognition. The fMRI data shows that this reward loop leaves a durable imprint in visual cortex. That imprint is real. The open question is contextual. When does it help? When does it narrow what you notice? That question is what we discussed here. We learn what trained us, and then we decide when to use it. Hopefully being more aware of the patterns with which we approached problem solving that we developed in our youth and in our experiences can help us be more aware of how our brains are interpreting problems and allowing us to add 1 second check on ourselves to see if, instead of narrating our problems to ourselves, we can monitor and check to see if this approach is really paying off.